This lecture is a rough one. I wasn't really sure when to start this one. I'm putting it later after I've tried to warm you up to limits because this is not a precise. It's called a precise definition of a limit. The intent here is to define this notation. Okay, let me just fix it. All right, so I'm going to use geometric intuition, hopefully, to try to describe this. Let me put a step before I get to the actual hardcore definition. X arrow A means X is getting closer and closer to the number A. What we need that to mean is that if X goes to A, so if X approaches A, then f of X gets closer and closer to the number L. Remember, f of X just stands for y value. So as X is getting close to A, Y is getting close to L. Let me draw a picture of this. What I want to do, we have, let me draw a graph. I think what I want to do right now is let me take all the numbers and anything out of here. So I don't want to show the grid. Let's see, I don't even want to show the numbers, and I'll do that also for the y-axis. No grid and no numbers. So let me make a copy of this thing. Paste it in. Now, let me make up, I'm just going to freehand draw some kind of a function. Oh, you know what else too? Let me get that out of there. I didn't mean to do that yet. Nope. That's going to still mess me up. Let me change this also to, I don't want the ticks on there either. Take it out of here also. All right, this is really all I want to do. All right, so suppose I have a function. Don't know what it is, but let's just say that it is y equals f of x. And let's say the number A, the target, resides here somewhere. Now, if you go up A, straight up from A, till you hit the graph, come to a point, it may or may not be there. Remember, we don't care if the point is actually there. But then if you come straight over to the left, at least in this picture, that is where the target y value is L. Now, I somehow need to make a relation between the x values and the y values that will show that as the x values shrink down to A, the y values close in on L. So let me show you sort of how it does. We allow a certain amount of error in how far away I am from y. In fact, classically, the amount of error the amount of vertical error varies plus or minus L plus or minus epsilon. Let me fix this one here. The letter epsilon is conceivably there a Greek letter. So we use E for something else, but here we have a Greek letter, epsilon, that we're going to use to stand for error. Now, in order to show that these will close in on L as x gets closer to A, we also go over here with these and find those x values. So let me go straight over here. So that hits on the graph there. Let me go over just a little bit, make sure I get to the graph. If we luck out, and this is a perfect, A is exactly in the middle of these two ends, then I will have found a number that corresponds to these epsilons, at least on the x-axis though, that will correspond directly to these epsilons. What we refer to that as this. This x value over here is A minus delta. The D probably because it comes before the letter E. But if you luck out, if A is right in the middle, then the amount that A varies, its error is plus and minus delta. So, if now I come back with a smaller amount of epsilon, see, let me see if I can grow this some here. See if I can zoom in. I actually did not want to do that. Well, that sucks. I didn't mean to do that. I just meant to bring it in. What if I come back then with a smaller amount of error? Let's call it epsilon 1. And then L minus epsilon 1. Well, you can see that if I need my error to be smaller, then conceivably, when I go to find the x values that these correspond to, I might luck out and get an A minus delta 1. And over here, A minus delta 2. Let me make that delta a little better. I didn't mean delta 2 actually anyways. A plus delta 1. So, if I can make that happen, so that if this next one I have a new epsilon that's even closer, I can get new deltas that are even closer that will show that the closing in on x is forcing the y's to close in on L. That's the whole idea. This is, in some sense, we're actually giving a mathematical meaning to what it means to be close. So, I'm not going to state the definition just yet. I am going to do some examples. Let me get back down to regular size. I'm going to do some examples that show how you can compute these things from a real graph. So, we'll start with the easiest possible example that you can come up with. And insert function. Let's do a 2x minus 3. A line. I can't think of anything easier to start off the discussion with. I do not want to show that thing, so I will hide that. All right, and suppose we are interested in the limit as x goes to 4. So let's consider the limit as x goes to 4 of 2x minus 3. Now, from our discussion, you happen to know that for a line, things that don't have breaks or holes, you happen to know that you can just take the number 4 and plug it in for x. So if you do that, you'll get 2 times 4 will be 8, minus 3 will be 5. So I want to show that as x gets closer to 4, y, which is 2x minus 3, gets closer to 5. So let me write that out. Show that as x gets closer to 4, y gets closer to 5. So, x gets closer to 4. How do you even talk about the distance between x and 4? Well, we use a notation like this. The distance between x and a is the absolute value of x minus a. So I'm going to use that. So I would like x minus, in this case we're doing, so in this example, for the limit as x goes to 4, 2x minus 3 equals 5. The a in question is the number 4, so I'm going to consider, x minus 4 equals the distance between x and 4. I want to find a relationship between the distance between that and the distance between y minus 5. So find a connection between the distance x minus 4 and the distance y minus 5. Well, let's see if I can connect one. If you look back at the picture that I had up here, I considered a to be the center of an interval that would stretch from a minus delta to a plus delta. I can rewrite that as this: x minus 4 in absolute value less than delta is no different than negative delta is less than x minus 4 is less than positive delta. Now keep in mind, delta is a distance, so negative deltas aren't even to be considered. Now I'm going to try to get x by itself by adding 4 to everything. So I'll have 4 minus delta is less than x, which is less than 4 plus delta. See, just like I mentioned in the picture, I have x is between 4 plus and minus delta. So the error on x is between 4 plus and minus delta. I got to somehow work this into y minus 5. Well, what is y? So if you remember, y equals 2x minus 3. So what I'm going to do is multiply everything by 2. So I'll get 8. Oh, I made it look like a delta, but that's not what I intended. I'm going to multiply everything by 2 because inside of here I want to get 2x minus 3. So if I multiply everything by 2, I get 8 minus 2 delta is less than 2x, which is less than 8 plus 2 delta. And then next, I want to subtract 3 from everything. So that'll put me at 5 minus 2 delta is less than 2x minus 3, which is less than 5 plus 2 delta. Well, what I had to get, now what I was supposed to get was this. Y minus 5. If you look back to the graph, the amount of error around, oh, no, that's not where it's at, is it? Let me go back up here. You go back to the graph, x was allowed to move between negative delta and delta. Y is allowed to move between negative epsilon and L plus and minus epsilon. So what I'm saying here, that is y right there. Y minus 5, the distance between y and 5 is less than epsilon. Or well, let me get rid of this. I'm going to subtract 5 from everything here. This here is y. Let me put that, I can't. Y. Okay, so let me write that again. 5 minus 2 delta is less than y is less than 5 plus 2 delta. Now let me subtract 5. I was supposed to get y minus 5. So if I do this, y minus 5 is less than 2 delta. And it's greater than negative 2 delta. Well, if you remember, y was supposed to go, the goal that we wanted, I'll put it over here, the goal was to try to get negative epsilon less than y. Yeah, y was supposed to go between 5 minus epsilon and 5 plus epsilon. Or y minus 5. If I subtract 5 from it, I think I want y minus 5 more. Y minus 5 is less than epsilon. I just noticed I made an epsilon into a 3. My kids would have a field day with that one if they knew I did that. All right, so y minus 5 negative epsilon. So if you compare these two things together, if you look, this guy right here, or better yet, I don't care about the negative version of it, this one here. You could see that the connection is 2 delta equals epsilon. Now, epsilon is given error, so your job is to find the x, or the x error that you're permitted to have. So if somebody gives you epsilon, you can say, well, the delta that I want is epsilon over 2. This gives a formula, and at the same time, it proves that limit. So let's give this a shot. What I want to do is consider that limit again. The limit as x goes to 4, 2x minus 3 equals 5. I already have the graph in the other screen. We'll go back to it in just a moment. Now, let epsilon equals 0.1. That's my error. And then from this formula up here, delta equals epsilon over 2, which equals 0.05. This is the amount of x variation I'm allowed to have. So when I go to the graph, and I specify my x and y values, I want the minimum. Well, let me go back here for a second. I will say that y is less than 5 plus 0.1 is greater than 5 minus 0.1, and x then, x is less than 4 plus 0.05, and greater than 4 minus 0.05. I'm going to use these settings on my graph. And you'll see what I'm talking about here, how they're perfectly connected. I have to change these, of course, to 4.99 is less than y, which is less than 5.1, and 3.95 is less than x, which is less than 4.05. So let me set my window to that. So for x, I said 3.95 to 4.05. And for y, that was 4.9, I think it's 4.9, not 5, 4.99. 4.9 to 5.1. Okay. If you look, this is important. I've perfectly captured that piece of the graph in this screen. Down here, let me copy and paste this thing. It'll take more than just the graph. Take a little bit more than it. But I need you to understand where these corners are. In this picture that we have here, this point right here, the x and y value is 3.95, comma 4.9, and up here, that point is 4.05 to comma 5.1. Do you see how they're perfectly connected to each other here? And this is the relationship I want to exploit, because if I go and change the amount of error I'm allowed, like last time the error was 0.1, well, what if I made it smaller? I want to keep this kind of a picture in mind, because if the y squeezes down, you need the x to squeeze down with it. So that way it shows a perfect relationship between the x and y's. As x gets closer to its target, y will get closer to its target. So I'm going to try a smaller epsilon with the same example. Let's let epsilon equal 0.01. So then delta equals 0.005. Now y was centered around 5, so we want 4.99 to 5.01 for y. And then x was centered around 4, so we would have 3.995 to 4.005. Let's throw those in. I should probably bring this down. It'd be easier if yeah, there we go. All right, so the x goes 3.995 to 4.005, and the y values go from 4.99 tab to 5.01. See what we got. And as you look, I changed the size of the screen right before your eyes there, and it didn't appear like anything happened, because once again, I've perfectly captured the x and y's that correspond to each other. So let's bring that up. I actually don't have to recopy. I could just copy the same thing I had before, but just to be honest. This is actually a different screen, but it looks identical to the one before, simply because the relationship we have found between the two of them is perfect. Now, this point down here was 3.995 and 4.005. No, sorry, 4.99. And up here, this point is 4.005, comma, 5.01. I'll put it in there. It's a very long video. I'll probably redo it and slice it up. But if not, if it ends up being like this, I'm going to end there because that's a lot to digest for now. We'll do more examples in future videos.